Okay, guys, now I'm going to start part 2 of section 3.3. Mhm. I was a little bit rushed at the end of the part 1 because I had to run for my class. So, hope you all understood that okay. So, this part 2 shouldn't be that long. So, there are only few definitions and one particular topic I need to cover. I will cover that and this. So, let us continue where we left off. So let us share and start with the same PowerPoint. Hope you all can see that. I think we left off right here, k-tuple coloring. Let us start with some definitions. You have a graph G will be given to you, and what is the meaning of subdividing the graph? I'll explain with the help of an example. Take a graph. What is the meaning of subdividing this graph? That means you are constructing another graph G prime. The only thing you're doing is take the same graph. This is like a 4 cycle, and you place couple of edges, a couple of vertices on some of the edges. Maybe I'll put one edge here, maybe I'll put one more edge there, and I'll put one edge here. You will call this G prime is a subdivision of G by placing on one edge. I don't want to put more than one edge, so let us erase this. This is called subdividing this graph G. That means this graph has 1, 2, 3, 4 vertices and 4 edges, whereas this graph has 1, 2, 3, 4, 5, 6 edges and 6 vertices. So I got this G prime by placing some vertices on one edge. So you will call this G prime as subdivision of G. That is the meaning of this. So hope you understood that. So you are placing some vertices on one of the edge. It's as simple as that. Now this is first definition. What is the meaning of two graphs are homeomorphic to each other? That means you start from one graph and go to the other by keep on subdividing it. Or another way you can think is you can get both of these from another graph by keep on subdividing it. That means you start with the graph H and you get G and also G prime by subdividing H. For example, take these two graphs. 1, 2, 3. This is a chain of length 3, and this is a chain of length say 5. You can get both of them. I'll call this as G and I'll call this as G prime. I can call both these is homeomorphic because I can get both of them from this graph H. I can get G from this by placing 2 vertices. I can get G prime by placing 4 vertices. So I can get both of them by keeping this as my starting point. So I'll call G and G prime are homeomorphic to each other. That means they have the same parent in a sense. Okay, so we got two definitions. What is the meaning of a subdividing a graph and what is the meaning two graphs are homeomorphic? Now one more definition is what is the meaning of contracting an edge from a graph? I will explain with the help of an example. Take a graph. So let us say this. Let us take this graph. Say I will call this as vertex A, B, C, D, E. Now this is my graph G. Okay. Now I am selecting this edge E. What is the meaning of contracting this edge means? That means you replace this AD with a single vertex. I call that as X. And A and D are now replaced with one single vertex. Two vertices are gone replaced by one, and all B, C, and E are already there. The vertices between B, C, and E will be there. Okay, let us add these two also. This is my graph G. So these will be there. Now A is connected to E, so X should be connected to A as well. And D is connected to B and C, so X should be connected to both B and also C. that should be connected to both B and also C. And so whatever A and D are connected to, this X will be connected to all of them. That means if there is an edge between A and D, there should be an edge between X and D. If there is an edge between D and B, there should be an X between D and B. And there is an edge between D and C, so there should be an edge between S and C also. And so this is called, this graph G prime, I'll call by contracting the edge E from G. For example, I'm saying if both A and D are connected to some vertex E, then you don't need to draw two edges. You just draw one. That is good enough. That's what this is saying. If both X and Y are joined to a single, then only one of the edges. You don't need to replace them with two edges. That is the meaning of contracting. Contracting G to G prime means, so if you do a sequence of contractions, if you end up there, then you will say you got G prime from contracting G. It is as simple as that. Okay, so hope you understood what is the meaning of contracting. So you have a couple more examples on page 153. So go to page 153. There are a couple more examples on that page. So just go through this definition. So there are three definitions we covered: subdividing, homeomorphic, and contracting an edge. So these are useful in our next topic, that is called the planar graphs. What is the meaning a graph is planar? That means if I can sketch the graph so that no two edges cross, then you'll call that graph as planar graph. A typical example, you see this huge graph, no two edges are crossing each other, only except at the vertices, so they're not crossing. So this is an example of a plane graph. For example, let us look a couple more. Let us look into this. Say take this graph. Okay, this is a complete graph on 4 vertices really. So K4. So this is, I'll call A, B, C, D. This is not a plane graph. It's not looking like a plane graph because these two edges are crossing each other, but I can redraw it and I can do like this. This is going to be there. Now no edges are crossing each other. Now I'll take from B to C and connect it like this. So both are exactly the same graphs, but this is called a plane drawing of the graph. And this is called, so that is the reason you will call K4 as a planar graph. That means I can draw this graph so that no two edges cross each other. So take any graph, if you can redraw it so that no two edges cross each other, you will call that graph as a planar graph. And do you think each and every graph is a planar? So take any graph, can you draw it like this? You can try a couple on your own. Before you go to the next page, please try a couple on your own. Draw a graph on your own and see whether you can draw them so that edges won't cross each other. So are there graphs which are non-planar? So are there any graphs which you cannot do this business? And the answer is yes. And the good thing is, a typical example of the two non-planar graphs are, one is going to be K5. This is a complete graph on 5 vertices. You try this. Try it. Can you, because see these and these are crossing each other, at least you will screw up in one place. This is called K33. You can try this. And I'm posting one more video on YouTube video and which talks about why K33 is not planar. So please go through that planar graphs video. It's just 5 minutes. So you can see that why this is not a planar as well. The proof I want you to try. So try to sketch the graph so that no two edges are cross each other. And the thing is, even if you remove just one of the edges, that becomes a planar. For example, let us go into the next page. I just removed the edge between B and C. Now I can redraw the same graph where the vertices are not crossing each other. So just K5 is a mess. Even just by removing one edge makes your life easier, in the sense it becomes a planar graph. So now go through the video which I posted on the planar graphs on YouTube. It will tell you why K33 is not planar and K5 is not planar. And the most wonderful fact is, these are the only two graphs which are not planar. In the sense, take K5. If I add bunch more vertices and add bunch more edges, that is still a non-planar because I cannot, there is a K5 which is hiding inside. Similarly, if you take K33 and add bunch more vertices and bunch more edges, as long as you don't mess this up, the resultant graph which has K33 inside is also not planar. But other than that, if the graph doesn't have K5 or K33 lying inside, that is a planar graph. It doesn't matter. It can have 1000 vertices and 3000 edges. Still, you can sketch the graph so that no two edges cross each other. That is a wonderful result. That is by Kortowski. What he tells is this. A graph is a planar graph if and only if it has no subgraph homeomorphic to K5 or K33. That means there is no graph which is inside, hiding inside, which I can convert it to K5 or K33. It might not be K5 or K33, but there is something lying inside. By subdividing it, that becomes K5 or K33. Then that becomes a not planar graph. It has no subgraph inside. Similarly, another result also, it is a planar if and only if it has no subgraph that can be contracted to K5 or K33. In a sense, these two results says this. If there is a subgraph inside the huge graph, somehow which I can change it to K5 or K33 either by subdividing it or by removing some edges, then that becomes a non-planar. Other than that, if there is no K5 or K33 hiding inside in any form, that is a planar. So a typical example, again, the proofs are beyond the scope of the book. The proof is by Kortowski and the proof is a little bit complicated. So even that is not covered in a graduate level course, so I'm not going to go through that. But there is a nice figure on page 154. You can please study that example. Again, they have given an example that is a complicated graph, and they showed there is a subgraph inside which is homeomorphic to K5 or K33 and which can also be contracted to this. So that is a non-planar graph. That means I cannot sketch its drawing. So please spend few minutes on this. And also please go through the video I posted, 5-minute video, and that sort of covers the planar portion. And I'm going to end this section with a nice result of 4-color theorem. What this 4-color theorem says is this. Take any map in the world, and it says I can color that map by using just 4 colors. That is in a nutshell. So what it says is, take any plane, and if I want to design, suppose this is the plane, and I want to color the plane so that if two regions which are adjacent to each other, and I have to give them a different color. That means, for example, take the world map, and I want to color the entire world map so that if the two countries share a border, then I want to color those two countries with 2 different colors. For example, if I want to color the world map, say Brazil and Argentina, they share a border, so I need to color those 2 countries with different colors. So what 4-color theorem says is, take any map, any complicated map, as long as you want to color them so that 2 adjacent regions has a different color, 4 colors is good enough. You can just, by using 4 colors, you can color everything. In fact, for almost all the maps in the world, just 3 colors is enough. There are very few of them where you need the 4th color. The graph theory version of this is this. For example, take this. Each and every region is denoted by a vertex. And if these 2 regions share a boundary, I join them an edge. So this is the region and this is this. Now coloring that region is exactly same as coloring the vertex. So all I am saying is I can give a proper coloring with just 4 colors. A typical example you can see, I just used 4 colors. So the graph you get like this from a map. So take any map, and for example, take the United States map. I just used 4 colors. You can see that each and every state is a vertex, and if 2 states share the border, you join them by an edge. For example, this Washington has no sharing border with Texas, so there is no edge connecting these 2. So this graph has 48 vertices. Oh, even I consider Alaska in this and Hawaii as well. So this graph has 52 vertices, and you join them by an edge if these two states share the border. So I can just use 4 colors. I can map the entire US map. And please remember, there might be some states which might share a corner. Then you can't apply this theorem there. So that means if there are countries like this, where borders are like this, if they don't share a region but they just share a tip, then it's not that they have a border. So here the border has to be more visible there. In a sense, it has to be a region. That is called the 4-color theorem. And the proof of the 4-color theorem is an open problem for almost like 100 years. In 1976 or 78, the first proof came by using a high powerful computer, and the computer ran like 1200 minutes or something. And most of the mathematicians don't consider that as a proof, because that computer is proved by checking all possible maps in the world. That is not a thing. When in 1997 a proper mathematical proof came. So this is still a very valuable and very popular result. That is called the 4-color theorem. You can Google it, and it's going to give you wonderful results on it. So, and one thing I want to mention, the map, the graphs you get from a map is always a plane graph. So another way I can say this is every plane graph is 4-colorable. Every plane graph is 4-colorable. So that is a nice result. I want to end this section. So we are done with 3.3. So I'll go and post 3.4, or I'll go through that and see whether that can be a reading assignment. So there are 3 videos. 3.3, I posted 2 videos, part 1, part 2, and one 5-minute YouTube video. Please go through them. I'm going to post an assignment sometime today. Thank you so much, guys. I stopped sharing this. I see. Now I stop.